Smale for so many years now, and we will talk about what we're doing tomorrow. Yeah. But now the next speaker is Dr. Chua. But interestingly, Michael was a TA for him long time ago. Long time ago.
E104, I think.
And in fact, Dr. Chua, it is interesting to see that one of your paper is some sort of a, Dr. Smale and I read many times recently about the Age of Chaos. So, and I'm excited to hear your talk. And this is Dr. Chua from here, University of Berkeley, Electrical Engineering Department. Thank you, Dr. Chua.
Thank you. Good morning. Let me try to get used to the pointer here. So what you see here, this is considered one of the most famous papers ever in neurophysiology, and this is the paper that led to the Nobel Prize. And this is the first page where of this paper that contains this famous circuit that you can see here. This is the famous Hodgkin-Huxley circuit, and there you will see two resistors with two arrowheads. And the reason the two arrowheads is because Hodgkin didn't know how to code it, because it varies with time. It's not an ordinary resistor, and so that is actually the problem today. What is this two time varying resistor? This is the equation for ODE from that circuit. And this is the classic Hodgkin-Huxley equation. The two time-varying resistors is embedded in two of these equations. And this equation is famous for being able to reproduce the action potential on the left side from that equation. So that's why it's so powerful, and it's a classic equation. Okay, now, but there is a problem with that circuit. Hodgkin-Huxley called it anomalous, in fact, because Hodgkin and Kenneth Cole on the right is a professor from Columbia University. When Hodgkin got a fellowship from England to visit USA, he was collaborating with Cole, so they were very close to each other. So Hodgkin and Cole have independently measured from the squid axon membrane gigantic inductances in DCVI curves that looks like diodes. Now, when you say gigantic inductances, that means that they actually measured them, and it's something like 0.5, even 1 Henry. And just to get a feeling on what's 1 Henry, by the way, this is a caricature of the brain, and you can see if indeed they are inductors, huge inductors, you ought to be seeing magnetic fields everywhere. But Hodgkin and Huxley say that where are the gigantic magnetic fields and the rectifiers? And I'm carrying, just to show you what 1 Henry inductor. I'm carrying about a 1 Henry inductor. So that's it. It's just imagine our brain will be carrying tons of this thing. Okay, that's a problem. Okay, so Cole is famous for saying that the suggestion of an inductive reactance anywhere in a system was shocking to the point of being unbelievable. Although Hodgkin and Huxley, wait a minute. So I said that Hodgkin had struggled in vain searching for the physical interpretation of the squid axon inductance. He failed because he had mistaken the axon for time-varying conductance, or he called them time-varying conductance. when in fact it has a simple explanation if the potassium and sodium ion channels are identified as memristors, which is part of my title of my talk. So what I'll show you now is the upper part is the Hodgkin-Huxley original circuit, and the anomalous conductances on top should be replaced by two memristors, actually, by one memristor at least down here, and there's sorry.
So what is a memristor?
I'm going to define what it is soon. Okay, so this element, time-varying conductance, is now going to be replaced by a sodium memristor, and this potassium conductance is going to be replaced by potassium memristor, and they have exactly the same equation. You saw the Hodgkin-Huxley equation. If you extract them, instead of using it here incorrectly, they actually define uniquely these two memristors. So nothing is changed. Equation is unchanged, except that everything is made correctly, is identified correctly. Now, it turns out that there was a crisis. There was a crisis in these time-varying conductances, and I had to develop a new theory, what I call the axiomatic approach, to define these four elements. So look at this. Take any black box with two wires coming out, and there are four variables: fundamental voltage and current, the V and I. And if you integrate the current, you get a charge. So that's the third fundamental variable. If you integrate the voltage, you get a flux. These are the four fundamental circuit variables in my axiomatic definition of circuit elements. Now, see. Wait a minute. What's going on? Something is not right here. I think I need some help.
Yeah.
How do I get, after that it comes back? Okay, thank you. So from the four fundamental variables, this is how I define, which is the proper way of defining circuit element. If you relate two of the four variables by a relation, a mathematical relation, such as the first one, a relationship between the voltage, a relationship between the voltage and current, such as this relation, that element is called a resistor, and that would be the symbol. If the relationship is instead between the current and the flux, that element is called an inductor. If the relationship is between voltage and charge, that element is called capacitor. These are the correct definition, axiomatic definition of the three classic circuit elements. The problem is with this axiomatic approach is that there is a missing link down here. So, what is this missing link? The missing link is in fact the memristor. It's part of my lecture today, and you will see that memristor is in fact a very fundamental circuit element. that is going to be widely used. It will be a future workhorse for other artificial intelligence. You heard a lot about the data centers that consume hundreds of kilowatts of power. It's going to eventually make use of memristor that greatly reduce the power, for example, and many other applications. So I'm going to say, so what is a memristor? Roughly, a memristor is a two-terminal device whose resistance can be tuned to some desired value by applying a voltage signal, and which remembers its resistance after the voltage source is disconnected. In other words, it remembers its past. So a typical example of memristor would be, for example, a curve like that between flux is a relationship between the last two variables, flux and charge. And any such relationship defines a memristor. And the slope of that is the time-varying thing that Hodgkin used incorrectly. So the memristor is characterized, in fact, just like Ohm's law, V is equal to Ri, except that the resistance is a function of one of the two variables. In this case, is the charge. In another example I will show you, it will be the function of flux. So that's the definition of a memristor. So I published this paper in 1971, and it was forgotten because there was no solid state device that exists at that time that has this property. But fast forward to 2008, there's a paper in Nature with the title, "The Missing Memristor Found." And this is what opens up the whole new area. This is one of the picture of an array of memristors. This is an array. Each one of these white dots is a memristor, and the size is 17 nanometer. 17 nanometer. Just to show you a comparison, what's 17 nanometer? For those of you that don't have a feeling, this is the smallest virus, and the smallest known virus is about 25 nanometer. So each of these memristor is already smaller than the smallest virus. So this is just an array with a density indicated there. But today I'm going to show you the state of the art, where we're talking about 100 million memristors. So the memristor obviously is an acronym for memory resistor. Now I'm going to move on now to, you see here a picture of a slug, a sea slug called Arplegia. And you will see that he's wearing a Nobel Prize medal. And that's because Eric Kandel, who got the Nobel Prize, wait a minute. Eric Price, when he went to accept the medal to give a talk, he flashed this picture and showed him that his success depends on everything that he learned from Arplegia. Now this is the interesting thing. The Arplegia has a gill for breathing, for breathing, and there is a siphon that sends for any source of danger. When there's any danger, it will send a signal, and this thing will withdraw and close. So that's how it works. So what the experiment Kandel did is to send in some shocks, and every time a shock, he measured the signal that came out of the shock. So this is the actual picture from Kandel. He put in 15 shocks, but he showed you only five of them. See, they're all identical shocks. And then he monitored and record what is the corresponding response. And this is the first response is this one. And the next, remember, the shocks are all identical, the signal, but the next response becomes a little bit smaller. And then these are the second response. The fifth response is even smaller, and the 10th even smaller. And so Eric was shocked and realized that this is something very deep here, because the Kandel is learning that it is not so dangerous anymore, so there's no reason to hurry, to decrease. And that is the basis of the Nobel Prize, in fact. Of course, the tons of new results came out from this experiment. Now, we turned out that these are synapses. In fact, wait a minute. So this is a memristor, and this is the charge versus flux curve, and this slope, decreases monotonically. So this is just an imitation of the experiment. So you have 15 pulses, identical, and then you measure the response, and the first one is large, and the next one kept getting smaller and smaller, and in fact the corresponding 5 measured response correspond to what you can see here. So this memristor, in other words, is exactly what the appreciation is showing. So essentially, we just show you that the synapses are memristors. And the next example is another Nobel Prize. In fact, it's earlier, 1973, by Josephson, Brian Josephson had a Nobel Prize, and here's another circuit that get him the Nobel Prize. The circuit consists of a capacitor, a resistor, and an element that Joseph didn't quite have a name. We now know but it's a relationship between current and flux, and we know that that's an inductor. So that's an inductor. But Josephson was a little bit sort of embarrassed to say that there is actually a small current, quite negligible, but he said, to be honest, there is another current that he didn't know what it is, but he has an equation based on quantum physics on quasi-particle interference, and he says it obeys the equation current is equal to something times the voltage, and that something is something that's proportional to flux. Well, we now know, of course, that is a memristor. So the correct, complete Josephson function model consists of these 4 elements, the inductor and the memristor. So there's a second example where memristor plays a major role, because that's what it is. The next experiment is another Nobel Prize, and dates back even earlier. It's 1904. This is Pavlov. Pavlov is famous for this experiment that led to his Nobel Prize. You see a dog here, and his Pavlov's stuff, and Pavlov was trying to observed the behavior, the response of the dog to different kinds of excitations. So he showed it, ring a bell, the dog is indifferent. But when he shows a piece of meat, the dog salivates. Then Pavlov did the following impressive experiment. He showed the dog with the bell and the meat at the same time, and of course the dog salivates. And then finally, when Pavlov showed only the bell, the dog salivates. So he has learned that was the first experiment that demonstrates associative memory and learning. Associative memory and learning is in fact defined as the ability to learn and remember the relationship between unrelated experience or events. In fact, even as early as 350 BC, Aristotle already suggested that learning involves an association of ideas. And in as recent as just we published a paper where we have a single memristor. This is in China, Wuhan, China. A single memristor produced in the lab of Professor Miao. I was a co-author just for courtesy. I did very little. Okay, so this first voltage source is the analog of the bell. The second voltage source is analog of the meat. And when this is the memristor, and it turned out that this exactly reproduced the Pavlov experiment, the measurement. So we just showed that memristor is also a fundamental element for associative memory. Now, so let's go back to Hodgkin-Huxley circuit. Now we use the correct model, and now we applied a DC current, DC voltage plus a perturbation, and measure the corresponding current, DC current, and the current perturbation. And from that, you can derive what's called a small signal circuit model of the global circuit. And this circuit is interesting because this is now linear model, and I want to call your attention that there's an inductor and a resistor, and both of them are negative values. Okay, and this is now sophomore circuit theory. You can calculate the admittance, which is the Laplace transform of the variation of current and Laplace transform variation of voltage, and you will get a typical admittance. In this case, this is the function. And I call this a complexity function because this same approach applies to systems that have nothing to do with electrical engineering. So this is a general result. Now I'm going to give you a glimpse of edge of chaos in the form of a theorem here. The Hodgkin-Huxley edge of chaos criterion. It says that the Hodgkin-Huxley neuron under synaptic input V, the voltage out, is on the edge of chaos. So this is the theorem. But you can take this as a definition of view, which now what edge of chaos is, because this is the last part of my talk. Edge of chaos is going to be a very fundamental new concept for many of you. So this is the theorem. Say you're on the edge of chaos if two conditions are satisfied. First, all the zeros of the complexity function are in the open left half plane. So this is a stability condition. That's a well-known standard. The most of you, of course, no surprise. But what's new here, is that the real part of the complexity function is negative for at least one frequency. That is new, and that is the fundamental new result for defines edge of chaos. It turns out that testing therefore edge of chaos involves only linear algebra. And for example, we can quickly, for an input sample of 5 some volt here, you can quickly calculate the real part and the imaginary part of the complexity function, the admittance. But it's more convenient to plot it in the polar plane, the imaginary versus the real plane, and circuit theory calls this a Nyquist plot. So this same information is translated into this, and now the edge of chaos is now simply saying that Hodgkin-Huxley model is on edge of chaos at this voltage if its Nyquist plot intersects the imaginary axis. So the test becomes so obvious. You plot the Nyquist plot, and if it intersects the real axis, the system, in this case, not Hodgkin-Huxley equation, is on the edge of chaos. That's what it is. Okay, and this is applicable to tons of other examples now. Now, this is a caricature of the summarize the result of the edge of chaos, and you can see that the test shows that the edge of chaos is in a very tiny interval. It's 0.00 millivolt, or in terms of current, it's 1.94 microampere. This is to show you that the edge of chaos is typically a very small region. And unless you have a method to calculate it, you will not be able to find it. And we do have that method, as you can see already. And so I call this the Goldilocks zone for action potential. And the window for life to be possible is that either the current should be less than 2 microampere or the voltage is less than 1 millivolt. The active, now the next important result is called this a principle, but it's actually a theorem. It says that all devices or complexity function or circuit, let's call it circuit device with 2 terminals, is either locally passive or locally active, and within the local activity there is a tiny region which of course I exaggerate so you can see. It's called the edge of chaos. And all the complexity, all the thing that make life possible is in that region. And we have constructed a method to test, to derive this region. That's one of the main results today. And the local activity theorem is stated here, but I don't have time to go through it today, but just to tell you that this is a necessary and sufficient condition. The physical meaning of activity is that one can use a locally active cell to amplify small signals at the expense of an external power supply. For example, neurons in our brain maintains the local level of organization by burning glucose. In fact, every living cell is a molecular amplifier. Action potential is impossible without edge of chaos. Neuron, therefore, is poised near the edge of chaos. And local activity is, in fact, the origin of complexity. Now, I want to fast forward to tell you the state of the art. In Nature, 2023. What? Oh, I'm going to need another 10 minutes. Is that okay? Because otherwise you go. Yeah. I just want to tell you This is the state of the art. 2023 in Nature shows that the real memristor with thousands of conductors has been made, and there is this picture of that a wafer that contains 1 billion memristors, and this can be used now. For example, you can use that to solve Navier-Stokes equation. Instead of solving it by MATLAB, you can see you get the same result by the fractions of the time. But I have to tell you, I need another 5 minutes to Turing. There was a month ago, less than a month ago, there is a BBC announcement and published in Guardian showing that accidentally discovered some old papers by Turing, including his PhD thesis. And his PhD thesis, in fact, has now, oops, sorry. The PhD thesis was auctioned for something like 129 euro, and then there's, for today's talk, the chemical basis of morphogenesis, which is really what I want to talk about in 5 minutes. This was auctioned for $22,000, and so let me now. So I'm going to just quickly mention Steve Mayer's famous paper. He says that various forms of Turing equation or reaction diffusion equation have appeared in one form or another in many works and fields. However, any sort of systematic understanding or analysis seems to be far away. Before one can expect any general understanding, many examples will have to be thought through, both on the mathematical side and on the experimental side. And I want to tell you that this has been done within the last 2 years already, and I just quickly flash to you. So this paper says age of chaos is sine qua non for Turing instability, and there's a circuit. So Steve was asking for both experiment and theory. So this is the experiment, and the circuit there is used, and this is from Professor Wang and Jay Jin from Hangzhou University, and this is the circuit with 2 memristors, and it produces exactly what Smale was asking for. This is the experimental result that proves Turing instability. And finally, Steve also said that there is a paradoxical aspect to the example. One has 2 dead mathematical cells interacting by diffusion process, which has tendency in itself to equalize this concentration. Yet in interaction, a state continues to pulse indefinitely. This is generally called it Smale Paradox. And now this paper has been published to show the Smale Paradox, and we have finally a circuit that's built. And this is the circuit that's in here, if you want to see here, that demonstrate this Smale Paradox. And this is the final example to show you that you before you do the coupling, there's only constant equilibrium. But once you exceed the the threshold that's calculated by the edge of chaos, this circuit, the two cells oscillate. And finally, I end up with one last Nobel Prize paper. This is a talk given by Geoffrey Hinton, who was the great-grandson of George Boole. Like all of you know. And George Hinton received the Nobel Prize before he gave this talk. Now, this talk says that a new type of computer, and the talk was given on December 22, and he got his Nobel Prize a year actually later. And I want to translate and quote what the last sentence of Geoffrey's talk is: computation, and he talked about a future, a new type of computer. He said, we are going to do what I call mortal computation, when the knowledge that the system has learned and the hardware are inseparable. If we do that, we can use very low power analog computation. You can have trillion-way parallelism using things like memristors. Thank you very much. Yeah. Those of you who want to stay behind after the talk, you are welcome to look at this.
Thank you so much.
So can I leave it here for now? Can you take it out? Then
Take it out.
take it out.
And the next speaker is Dr. Anthony Block from University of Michigan.
I'll take care of Steve.